Welcome, everyone. Thanks for coming, braving the winter rainstorm that we have. As you may have guessed, we probably aren't going to have observing tonight because of the cloud conditions. I'm Dr. Cameron Hummels. I'm a staff scientist here, and we've got a great program tonight. Just a couple quick announcements. One, at the entrance, there were posters or flyers that you were welcome to take. They have our schedule for the next 6 months or so. After Rachel's talk tonight, we have an event in 2 weeks' time by a visiting professor from Berkeley on the binary neutron star merger that occurred about a year ago. And then 2 weeks after that, we have another lecture given by Professor Mike Brown in the Planetary Science Department talking about the search for Planet 9, this new theoretical planet in the outer parts of the solar system. He's also known as Pluto Killer because he's responsible for much of the demotion of the planet Pluto and no longer being considered a full planet. On the backside of that schedule, we have our Astronomy on Tap series, which is another monthly kind of informal lecture series that takes place at a local bar in Old Town Pasadena, and our next event is in a week and a half. It's a week from this coming Monday, and that event is our first foreign language event. It's going to be entirely in Spanish, so I encourage you to come. Particularly if you speak Spanish, and to spread the word to other Spanish speakers that you think might be interested in attending. But all the information is on the flyer as well as on our website. There's also free swag. We have this NASA image of it's taken by the Spitzer Space Telescope of an object called M82, which is going to be featured in Rachel's talk tonight. It's a very active galaxy in the local universe. And yeah, I think those are all the announcements. As I said, we probably won't do stargazing, but Rachel will have roughly a 30-minute lecture, and then after we take some questions, we'll open things up. We'll move the table here and have a panel Q&A with much of our panel being graduate students and postdocs from within the department who have a number of different specialties on various different topics. So you're encouraged to ask questions on whatever topic in space science or astronomy or physics that you might have, and we will do our best to answer all of your questions about the cosmos. So, one additional announcement. All of our lectures have now been uploaded by wonderful graduate student Mike Jang to YouTube. So you are encouraged to search for Caltech Astronomy. Yeah, wave your hand, Mike. Thank you for your Herculean efforts. So if you go on YouTube and search for Caltech Astronomy, all of our lectures that we've had over the last 3 years are available, and you can watch them and share them and, yeah, have fun. So without any further ado, our speaker for tonight is soon, in maybe a year or so, will be a doctor. So Rachel Theios is a graduate student, fifth-year graduate student here. She grew up in Napa. She did her undergrad at UCLA, and now she's a graduate student focusing mostly on galaxy evolution and galaxies at an earlier epoch in the universe, which she's going to talk to us about tonight. So please welcome soon-to-be Dr. Rachel Theios.
Yes. Perspective, Dr. Hi, everyone. So the title of my talk is The Universe at Cosmic Noon. So the first question you're probably wondering is, what is cosmic noon? So this term came about because astronomers have been using the term cosmic dawn to refer to the period of time shortly after the Big Bang when the first stars and galaxies turned on in the universe. So cosmic noon is just some time after the cosmic dawn, and I'm going to talk about why it's interesting later in this talk. So first I'll start with a brief overview of the history of the entire universe. So this schematic shows basically time progressing along, okay, this is my project pointer, along this axis. So we start with the Big Bang 13.8 billion years ago, and at some point after the Big Bang, the first stars in the universe turned on. So we think that the universe was originally a big soup of atoms or protons and electrons that coalesced into atoms as the density of the universe decreased or increased. And then there was fluctuations in density, smaller or like less dense patches and more dense patches. The more dense patches collapsed under their own gravity to form stars. And so at this point in the diagram, the stars turn on. And so today, most stars we think are in galaxies. So these big, giant structures full of lots of stars separated by mostly empty space. But how did we get from the first stars turning on to the galaxies that we see today? And this topic of the formation of galaxies is a broad and active topic in research today. And the first stars, of course, will have died at some point, and then new stars will have formed. So these galaxies today have a rich and interesting ecosystem that is going to be the subject of my talk, and it's a topic of active research. So what is in a galaxy? Does anybody know what galaxies are made of? Anybody want to contribute? What? Black hole? Yeah, okay, I'll talk about that later in the talk, but that's a good one. Anything else? There's an obvious one. Stars, yes, stars. So you hopefully all know what stars are. They're just big balls of plasma that it's burning hydrogen to helium and emitting a lot of light, and that's what most of the visible matter in a galaxy is. Anything else? Yeah. Dust, yeah, that's my third item, and they pop up in a particular order, but I will get to that one. Anything else? Gas, yeah, gas is the next one. So gas, we think, is just gaseous matter, simple atoms and molecules that permeate the part of the galaxy and form new stars. And then dust, it was already mentioned. Dust is just more complex atoms and molecules that obscure light. And so if you look at this image here of the Milky Way seen from a very dark place, dust is kind of this dark band here, and that obscures the light from a lot of the stars. And there's one more thing on my list. Anything else? Dark matter, yes, that's good. So dark matter, we don't know what it's made of. We just know that it exists because of the gravitational pull it exerts on the normal matter. So we think that dark matter actually collapsed first under the weight of its own gravity, and then the normal matter fell in under that gravity to form stars. So dark matter is very interesting. I'm not going to talk about it a whole lot, but it is a really active topic of research, and we don't know what it is yet. So the main criterion for all these things actually being a galaxy is that they're all held together by gravity. So you don't have just stars randomly flying off into space. I mean, you sometimes do have stuff flying out into space, but that's an exception that I'll talk about later. And so based on the fact that when we look at the Milky Way, we see this plane or this band of stars going through the whole sky, we might infer that we're in some sort of disk-like structure or a plane. And in fact, when we look at galaxies outside of our Milky Way, we see that they fall into two main categories. And one is called spiral galaxies, like our Milky Way. So these have a disk-like structure with a nice, pretty spiral arms. And then in the center, there's a spherical bulge of stars. And then surrounding it is a halo of dark matter and also a few stars. And these are rotating about their center. They have a lot of active star formation and gas and dust in their disk. The other type of galaxy is called an elliptical galaxy. And these are basically just big blobs of stars. They can be really, really big. There's not a lot of ordered rotation. There's just random motions of the stars going in and out of the galaxy. There's not a lot of active star formation or gas or dust. And these things can be very, very huge. But there are also a few other types of galaxies. Irregular galaxies that just look like kind of also blobs, but more like spirals. Dwarf galaxies, which are just kind of sparse collections of stars, are very small. And these things that look like two galaxies merging together. And if you want to get involved in real science, you can go to a website called Galaxy Zoo, where it'll show you pictures of galaxies, and you can classify them into whatever type they are just by your eye. And then this actually helps astronomers because it's hard to classify galaxies in large numbers with computers. This is a fun thing you can do. Okay, but what do early galaxies look like? This is the topic that I'm going to talk about in my talk. Do they look different from galaxies today? Do they look the same? And if they're different, how did they evolve into the ones we see today? But first, I'm going to address the question of how do you actually look at galaxies that existed in the past? So there's a few aspects of physics that let us do this. First is that light has a finite speed. So the speed of light, I put it here in meters per second, but it's actually about 670 million miles per hour. It's pretty fast. So this means that when you're looking at a lamp in this room, it actually takes some time for light to get from the lamp to your eyes, and it's not a very long time. But the sun is about 8 light minutes away. So like a light year is a unit of distance. It's how far light can travel in 1 year. The sun is 8 light minutes away. So when you look at the sun, you're seeing it as it was 8 minutes ago and not the way it is now. So actually, if the sun exploded right now, we wouldn't know for 8 minutes, so stay tuned for that, the sun exploding. But stars and galaxies are much farther away. So the nearest star is about 4 light years away. The nearest big galaxy, similar to our Milky Way, is 2.5 million light years away, which is called Andromeda. So if you look at Andromeda, which you can see in a dark place with bare binoculars, you actually are looking at it as it was 2.5 million years ago. And so this means that the farther away you look, the farther back in time you're looking. So in order to look at forming galaxies at cosmic noon, which I should have said is to about 10 billion years ago. So cosmic noon, I'm calling is 10 billion years ago. To look at those things, you need to look 10 billion light years away. And that's pretty hard. But how do you actually know how far away you're looking? How do you measure distances in astronomy? I'm going to revise my schematic here. So time goes along this axis, but distance from Earth goes the other way. So you want to look at cosmic noon. You're going to have to look in here somewhere, so pretty far away. But how do you measure distances in astronomy? Well, to measure really far things, you have to use the fact that space-time itself is actually expanding. So if you've ever heard of Edwin Hubble, for whom the Hubble Space Telescope is named, a fun piece of Pasadena history is he observed, he actually discovered the expanding universe just from Mount Wilson Observatory right up that way, which you could see if it wasn't dark. So what he did is he measured distances to nearby galaxies using a specific type of variable star whose intrinsic brightness is known. So if you measure how bright or faint it is to your eye, and you know how bright it's supposed to be, then you can measure the distance, because things farther away are more faint. So he measured distances to these external galaxies, and then he measured velocities of these galaxies moving towards or away from us, which I'll get into how we measure those in a bit. But he found that not only is every galaxy moving away from us, the ones farther away are moving faster. So this is distance on the x-axis versus velocity on the y-axis. They're all moving away, and the ones farther away are moving faster. So the farther away a galaxy is, the faster it's moving away from us. And from this, he inferred that the universe is actually expanding. So how do you get from galaxies farther away move faster to the universe is expanding? Well, one analogy I like to use is the raisin bread analogy. So imagine you're in a loaf of raisin bread in the oven that's rising. So you're this raisin right here. And as the raisin bread dough expands, every raisin, including you, will see every other raisin moving away from it. Even the ones, this raisin and this raisin, they'll all see every other raisin moving away from them because the dough is expanding. And so from this, you can infer that the raisins far away appear to move faster, and that's what Hubble saw with galaxies. So the farther away a galaxy is, the faster it's moving away from us. This means that the universe is expanding like the raisin bread dough. And this also means that the Big Bang happened, because if you think everything is expanding, you might imagine there's a point in time where everything was in one spot, and you can trace back the expansion to zero. So the Big Bang happened. And then the next thing you can infer from this is that we can use a galaxy's velocity to measure its distance. So if you don't have these variable stars that you can see close by, you have to measure its distance using the velocity via this Hubble law that I just talked about. But how do you measure the velocities? So you have to use something called the Doppler Effect. So if you've ever been standing on the street and you hear an ambulance go by, you might have heard that the sound of the ambulance gets higher pitched as it moves toward you and lower pitched as it moves away from you. And I've kind of illustrated that here with the schematic. So the sound waves emitted by the ambulance get compressed along the direction that it's moving, and they expand to lower frequencies along the direction that it's going away from. And this actually applies to light as well, because light is a wave. So light emitted by a source moving towards us gets, the frequency gets shorter, so you get bluer wavelengths, and light emitted by a source moving away from you gets redder or longer wavelengths. And so how do we actually know? So we use that to measure, if you measure how much redder the light is than what you'd expect, you can get the velocity and therefore the distance to your galaxy. But how do you know what you expect the light to look like? And so you use the fact that different chemical elements emit and absorb light at specific wavelengths or colors. So in this diagram, I have a light source like a star, like the sun. If you ever looked at the sun through a prism, which you shouldn't do with your eyes, but you can disperse the light into different colors, and you can see that it makes a rainbow of light, so a continuous spectrum. But if you have a cool gas cloud or a cool stellar atmosphere in front of the star, the chemical elements in this gas cloud will absorb at certain frequencies. So you get a dark band superimposed on your continuous spectrum of light. So this is wavelength here, so blue to red, longer wavelengths. And then you have a dark band at one specific wavelength corresponding to whatever chemical element that is absorbing at that wavelength in the gas cloud that's cooler than the light source. But if you have a hot gas cloud and no light source, but the gas cloud is hot enough to emit by itself, you'll see a bright band at that same wavelength superimposed on just dark. So these are called spectral lines, absorption lines and emission lines. And so you know what these are supposed to look like based on what chemical elements you think are in your source. And we think galaxies have a lot of hydrogen because there's a lot of hydrogen everywhere. So if you measure a hydrogen spectral line and you find that it's redder than what you expect by some amount, you can use that to infer the velocity and therefore the distance to the galaxy. So these spectral lines will be redshifted, so move to redder frequencies because everything is moving away from us, as Hubble discovered. So the more distant a galaxy is, the more the light will be redshifted. And it turns out that at cosmic noon, which I've said is 10 billion years ago, it's redshifted so much that visible light from stars and gas that we can see with our eyes is shifted out of the visible portion of the spectrum into the infrared, which you can't see with your eyes. So if you've ever seen like a thermal camera, that's infrared. Your body is emitting in the infrared, but you can't see it with your own eyes. But, and actually, this makes it really hard to observe galaxies at cosmic noon because regular cameras don't work in the infrared. So there's a few things you need. You need a special detector that works in the infrared, and you also need a really big telescope. Since these galaxies are very faint, they're very far away, and you need lots of time on a big telescope to do that. But these technologies, really special infrared detectors and big telescopes, have advanced a lot in the last few decades. So these pictures here are the Keck telescopes on Mauna Kea in Hawaii, and myself and a lot of Caltech researchers use these telescopes. There's two of them. The mirrors on each telescope are 10 meters in diameter, so there's a human right here for scale. He's very small. They're very big mirrors, and you can collect a lot of light, and you can use these to observe forming galaxies 10 billion years ago at cosmic noon, and that is what I do in my research. Okay, so a recap, how do you observe forming galaxies? Step 1, point your telescope at a galaxy and make sure it's a big telescope with lots of time. Okay, we've done that. Step 2, measure how much redder the light is than what you would expect. And step 3, this gives you the velocity and therefore the distance, and you can use the finite speed of light to convert that into how many years ago are you looking at this galaxy? When did it exist in the universe? Any questions so far? No? Cool. Okay, so now that we've answered the question of how do we look at galaxies that existed in the past, we want to get into what do these galaxies 10 billion years ago look like. So this picture here was on my title slide. It's called the Hubble Ultra Deep Field, and you can't see it very well, but it looks like a field of stars, right? But it's actually everything in here, except for a few things, is a galaxy. So these are all distant galaxies. The Hubble Space Telescope pointed at this one patch of sky for a really long time and collected a lot of light to get all these distant faint galaxies. And so say we zoom in on one here that we think is at cosmic noon 10 billion years ago, and it doesn't look like a nice spiral. It looks very small, very clumpy, and very irregular. And we would expect it to be small and faint based on the fact that it's just far away. But actually, if you compare how big it is across relative to its distance, you find that it actually is intrinsically a very small, compact galaxy. It's not a big, pretty spiral like the Milky Way. It's a small, irregular, clumpy little thing. So these galaxies are small, faint, and irregular. So I'm going to make a running list, okay, of what's different about distant galaxies. First, they look smaller, fainter, and more irregular. But there's a lot of science that we can do, not just by looking at colors and shapes and pictures. So this is the only real graph I'm going to show in this talk. I will explain what's going on here. So on the x-axis here is distance from Earth, which I have converted to billions of years ago with the fact that light has a finite speed. So today is right here at 0. And then here's 10 billion years ago, here's 12 billion years ago, and then the Big Bang is like off over here off the graph. And the y-axis is the rate of stars formed, so number of stars formed per year in each of these galaxies, which are the data points. So what you can see here is that, here at whatever billion years ago this is, the rate of star formation went up and up and up, and then it peaked 10 billion years ago, and then it started to go down again until today. So now it's lower than it was in the past. So this peak, 10 billion years ago, is what I've been calling cosmic noon. So now it makes sense. Cosmic noon is the period of time at which the rate of star formation was at its highest ever. So it was never as high before this. It will never be as high again. This is the overall peak of stars forming in the universe. And actually, I think we think about half the mass in the universe today was formed in this rough area over here. So this is a really significant epoch. This is why it's so interesting, because a ton of the stuff that we see today was formed at this time, and it had a huge influence on how the universe looks today. Okay, so galaxies were forming stars at a faster rate. But we might ask, why is that? So I'm going to show this Hubble Ultra Deep Field again, but this time the purple is the same Hubble Space Telescope data that I showed you before, just stars. But overlaid in orange is radio wavelength light from cool gas. So this is like cooler gas that is what stars primarily form out of because it's cool enough to collapse under its gravity. It doesn't have a lot of thermal pressure, and it can condense and form stars. And so you can see that there's a few galaxies here. They're primarily the more distant ones that have tons of this cool gas. They're very bright in this orange. So we can infer from that that galaxies at cosmic noon just had a lot more interstellar gas compared to local ones. So there's just more stuff to form stars out of. And that's why there are so many stars forming, because there was a ton of gas, ton of stuff that you can just form stars with. So you're forming more stars than ever before. And this actually has an interesting consequence. The fact that there's so many stars forming at this epoch means that you get something called galactic superwinds. So the more stars you form, the more hot, young, massive stars you form. And these are the ones that blow up as supernovae. So supernovae are exploding stars that have reached the end of their life. and they collapse under their own gravity. They make a little core, and they explode, and they blow off, and they're very bright. They emit a lot of energy. And they emit so much energy that if you have lots of these going off all at the same time, you have enough energy to actually blow some of this interstellar gas out of the galaxy altogether. So this is called M82. This is the one that you can pick up on the little flyer out in the front that Cameron talked about. So you can see the galaxy is here, and there's this hot outflowing gas that we can see going off in either direction. And it turns out that we see these in the local universe. This is a very close by one, but there are a lot more of these galactic superwinds in the distant universe just because the star formation rate was so high. And this is actually what I study in my research right now. I'm looking at the velocities of outflowing gas in different components and comparing where did the gas come from originally in the galaxy, what's the distribution of different kinds of gas look like. And that's what I'm doing right now, so that's my research. Okay, so galaxies are forming stars at a faster rate. Why was that? Because there was more gas to form stars out of, and this makes galactic superwinds. So I talked about supernovae. They make these galactic superwinds, they blow gas out of the galaxy, but they also do more stuff than that. They make chemical elements. So this is the periodic table, color-coded by each stellar process or non-stellar process that makes each element. So you can see that the dark blue is the Big Bang. The only elements that are made in the Big Bang are hydrogen and helium. Those are the only two things. Everything else is made of stars. So as Carl Sagan said, we are all made of stardust. Everything that we're made of comes from stars, except for hydrogen and helium. But the type of stellar processes that these elements come from are different based, for each different element. So the exploding massive stars that I mentioned, the ones that really massive stars that die at the end of their life and explode as supernovae, these are color-coded in green. But there's a different kind of supernova called that's an exploding white dwarf. So a white dwarf is what we think the sun will turn into at the end of its lifetime. It will, once it uses up all its hydrogen in the core, it'll blow off all the gas on the outside, and the core will become this very hot, massive core. And then these things, they don't blow up normally, but if they have a companion next to it, they can accrete mass from the companion. We don't know fully how this happens, but once they get more mass, they blow up like a thermonuclear bomb in space, and it's very, very energetic. And these things have a known brightness. But they make different chemical elements than the other kind of supernova do. So in the local universe, we know what the relative ratios of these two types of supernovae are, and we can constrain what ratios of chemical elements we might see in the sun. But it turns out at cosmic noon, there were more of these green exploding massive stars and fewer of these blue exploding white dwarfs. And why is that? That is because they come from two different types of stars that have very different lifetimes. So the exploding massive stars come from very short-lived young stars. They're so big they don't live very long. They use up all their fuel very fast. The white dwarfs come from stars like our sun that are smaller. They have a lot more time to burn all their fuel, and they die a lot later. So at cosmic noon, there just wasn't enough time to form a lot of these white dwarfs and have them blow up and make all these elements like iron that we see from white dwarfs. So the chemical composition of galaxies at cosmic noon is going to be a lot different from those today. And this wasn't that really well understood until fairly recently. And a lot of researchers at Caltech have worked on this. And this is something that's been really percolating through the community very recently. But it's very important. The chemical composition of galaxies at cosmic noon is very different than the ones today. Okay, so galaxies at cosmic noon have different ratios of heavy elements. And now I'm going to switch gears for a bit and talk about something that everyone likes, which is supermassive black holes. Everyone thinks these are cool. So this is an artist's rendering of a supermassive black hole. This is from the movie Interstellar, which you might have seen. A physics professor at Caltech named Kip Thorne worked on this movie, and he put a lot of work into it. And so we think that this is probably one of the most accurate representations of a black hole ever. So here's the black hole. And a normal black hole is the result of a star collapsing. And so it has a mass of maybe a few times the mass of the sun or less. But these supermassive black holes have about 1 million solar masses. And I think someone mentioned in the audience earlier that we think these are in our galaxy. We do think every galaxy has one of these at the center. The Milky Way has one. We know it's there because of the way stars are orbiting around it. But some black holes have these accretion disks. So this is just stuff that's orbiting the black hole and falling into it. And as it orbits, it gets heated up, and it emits a lot of light at lots of different wavelengths. And so this circle here is just the backside of the accretion disk that we think is bent by gravity, so we can see it by the really strong gravity of the black hole, so we can see it on the top and the bottom. And that is a planet which existed in the movie, but we don't know if this actually exists around supermassive black holes in the real universe. So we don't know. But so the Milky Way, we think, has one of these, but we don't think it has a sizable accretion disk or a lot of stuff just orbiting the black hole and falling into it. But some galaxies have a lot of stuff orbiting and belonging into the black hole. They're actively accreting more material every day. And they emit lots of light at lots of different frequencies and wavelengths. And so this is an example of one in the local universe. So here's the galaxy here. You can see these bright jets of radio waves coming out. And those are just jets of like really high energy particles that are spewed out by the black hole along the kind of polar directions. And these are called active galactic nuclei. So they're just galaxies that have a very active supermassive black hole that's just eating a lot of stuff all at once and emitting a lot of light. And so not every galaxy has one. There are some that we see locally, but there are actually a lot more of these at cosmic noon. And in fact, there were a lot more of these then than there ever were at any other time in the universe's history. So not only was this the peak of star formation, it was the peak of the activity of these active galactic nuclei. So more supermassive black holes were accreting more stuff than they ever were before. And there are a lot brighter ones of these than we see now also. Okay, so more galaxies at cosmic noon have active galactic nuclei. So now that we've established that distant galaxies look very different from local ones, I want to answer the question of how do they turn into the galaxies we see today? And so that is actually an open question. We don't really know. There's a lot of different physics that goes into galaxy evolution, and there are a lot of different pathways by which galaxies can form. And this is something that's being studied by many different researchers all over the world, and it's not totally well understood yet. But I'm going to talk about one pathway just as an example that we think is important, and that's mergers of galaxies. So mergers of galaxies are one important pathway. And there are two different types of galaxy mergers that we see. So one is called a major merger. This is where, as you can see here, there's two really big galaxies, and they're kind of colliding, and they're going to form one even bigger galaxy, which we think will be an elliptical galaxy. So like the ones I showed you before that are just a big blob without any disk-like structure. The other kind is called a minor merger. So this is where a big galaxy basically eats a small one. So this is Andromeda, our nearest neighbor. And pictured here are two satellite galaxies. So they're small galaxies that are in the gravitational influence of Andromeda. And we think someday Andromeda is going to kind of consume these and eat them and turn into a, grow itself that way. And the Milky Way, in the Milky Way, we actually have evidence that the Milky Way has been eating these smaller galaxies. So this is an artist rendering of what this might look like. So the Milky Way has galaxies, or satellite galaxies, and when they fall into the Milky Way, they get stripped into these long streams along the direction of their orbits, and these are called tidal streams. And we actually see quite a few of these around the Milky Way. You can go on Wikipedia and just look up lists of tidal streams around the Milky Way, and there's a ton of them. There's lots of them. And these streams, because they're formed out of different galaxies, they're going to have different chemical compositions than the rest of the Milky Way. And so we can look at these streams, look at what kinds of stars and gas are in them to determine what the galaxy that it formed out of looked like. And we can use this to disentangle the merger history of the Milky Way. So that's just one pathway by which we can study galaxy evolution. And people at Caltech are working on this. But there's a lot of different physics that goes into this. There's a lot more pathways by which galaxies can form. And so finally, I'm going to end on a movie from Cameron here. Where's Cameron? Over there. This is Cameron's movie. So it's going to show a galaxy forming over cosmic time. So this left panel is color-coded by density. So the more dense regions are going to be in white, and the less dense are in black. And the right panel is the temperature. So I'm going to start it. So you can see that this galaxy is growing. There's kind of gas here along filaments that's kind of going into the center, and then it's blowing out all this very hot stuff here. And you can see here's the galaxy that's forming. It's accreting all these little small things, maybe bits of gas or more galaxies. You can see them falling in. And as cosmic time progresses, it's going to form a nice little disk-like structure, and it's going to rotate. So you can see it's more of like a spiral galaxy now. So yeah, maybe Cameron can say more about that. But that's just like we can study the evolution of galaxies by looking at computer simulation. So basically, you input your physics, you input your initial conditions, and then you evolve it over cosmic time to see what happens to your test galaxy. But obviously, there's a lot of stuff we don't know, and we don't know if the initial conditions or the physics are right. So there's a lot of active research going into this, but it's a very interesting way to study galaxy evolution. So in summary, why do we care about cosmic noon? Galaxies were forming stars at the fastest rate ever, so it has a really big impact on the way the universe looks today. How do these galaxies look different than the ones today? They are very compact, messy systems with lots of gas and young stars and different chemical compositions than those today. And finally, how do they evolve into galaxies today? We don't fully know, but we think mergers of galaxies are very important. And so I'll end with this. Cosmic noon was a busy time in the universe's history, and it had profound effects on the way galaxies look today. So thank you, everyone. Okay. So, any questions? Yeah.
The matter-antimatter asymmetry, was that an important issue in cosmic noon?
Matter-antimatter asymmetry? I don't think so. I think by that time everything was basically matter and there's very little antimatter. I think that much earlier, yeah. So at this period, things were still in galaxies. They were just very different galaxies than the ones today. So it wasn't like very, very early. This is about a few billion years after the Big Bang. So that would have been more important, like very early on, probably. But yeah. Any other questions? Yeah.
The trend of fewer and fewer stars forming as time goes on.
Oh, I meant to explain that. Yeah. So basically, you can just explain that. What was I going to say? So the fact that galaxies had more gas earlier on, they basically just used up a lot of their gas into stars, and there's not as much new gas to form stars out of. So basically, they kind of just ran out of fuel as time goes on, and eventually we'll just, every galaxy will be a galaxy, and then they'll all kind of expand apart under dark energy, and then heat death of the universe. But yeah. Your question?
Was,
okay.
Is there any sort of will it eventually plateau, or will it just continue down?
I think eventually it will just go to zero because everything will be in stars, and then the density will expand enough so that the universe will expand enough such that you can't actually form stars because there's just everything's too far apart and the dark energy is too strong. So I think eventually it would just have to go to zero. Does that make sense? Yeah, because you're not going to form stars forever. I mean, eventually everything will just die. But yeah, very sad. Yeah. Yeah, in the back. How big was the universe? Well, that's hard because we don't actually know how big the universe is. We just know how far away we can see because we can't see beyond. So basically, we can't see beyond 13.8 billion light years away because that's when the Big Bang happened. So there's no light that can get past us at that time, can get to us from earlier than that time. So we don't know how big the universe is.
With the instruments we have now, how far can we see any distance? With Hubble and Keck and all the others, what's our distance? What's the distance?
Well, so there's the cosmic microwave background, which is the farthest that you can see, and that's actually emitting thermal radiation in microwave wavelengths. It's coming from gas that's about 2.7 Kelvin. And so you can see that with space telescopes like Planck and WMAP. They can see this background radiation, but you can't see beyond that because before that, the universe was not neutral atoms. It was ionized, just plasma, and then light could not travel through that and get streamed through to what we can see today. So there's a fundamental physical limit to how far back we can look, and that's the cosmic microwave background.
So, okay, that is our physical.
Yeah, that's it.
13 billion years?
It's. I don't know how many billion years ago it is. I know the redshift, but does anyone, Cameron, do you know?
It was 300,000 years after.
Okay, yeah, 300,000 years after the Big Bang. That's good. Yeah. Any more? Yeah, I know.
Do you think that there will be a new way to measure time other than light years anytime soon?
Well, we don't measure time in light years. I mean, light years is a unit of distance. So light years is how far light can travel in 1 year. And there are a lot of other units of distance that we have in astronomy. They're kind of more complicated to explain. But that's just one unit of distance. We don't have any way of measuring time besides using like atomic clocks and things like that. But relativity complicates that a lot. I don't know if I want to get into that. Yeah. Yeah.
Well, I guess you could call it right now like the age of stars.
Yeah. It's the stelliferous era. That's the word for it, but it's a very fun word. It's called the stelliferous era. Nobody uses that word, but it's a very fun word. I like it. So.
You go back in time.
Yeah. Yeah.
Say shortly after the Big Bang.
Yeah.
There were no stars.
Right.
I don't know what you would call that era, but
There's a word. I don't know what that is, but yeah. It's just atoms floating around in space, protons, electrons that condense into atoms, and the dark matter. Yeah. But.
I guess if there were, I know there weren't, but if there were physicists living back in that time before there were stars,
Yeah.
they would look at the universe. Could they predict? You know what? There'll be stars. Of course, they wouldn't call them that. They predict that there will be stars. And so
I don't know. Yeah.
But can we predict that there will be some kind of other thing that's dominant in the universe? Other than
Well, we think dark energy will be dominant. So dark energy is, we don't really know what that is either, but it's just a force, or it's a force that just makes the universe expand and accelerate as it expands. And so eventually that will become dominant. That energy from that force, whatever it is, we don't know, will dominate over gravity, and then everything will expand away from each other. And so even galaxies will get ripped apart, and then you'll just have black holes floating around in space, and that's it. Yeah. The dark energy, or I don't know what's the word for that is, but yeah, that'll take over at some point. Yeah. Mm-hmm. You were, I think, raised your hand first.
do all galaxies need a supermassive black hole in time?
I don't think they need one. I think we just think most big ones have them, but I don't know. We don't fully understand how they form. I mean, there are many different speculations and ways people think they might form, but we're not like 100% sure how those things form. But they basically, it would just be a lot of smaller things coalescing into one big thing. But I don't think that's like a requirement. We just think that every galaxy does have one, if that makes any sense. Yeah. Oh, yeah.
Yeah, astronomers have been taking beautiful pictures
Oh, yeah.
for 100 years now.
Yeah.
Have you been able to see any change in the galaxies at all in terms of rotation or star movement, that type of thing?
You mean over the last years that we've been taking images? 100 years.
Compare the Hubble photos with what we have today. Do you see any changes at all?
I don't think you can see changes in individual stars, but you can certainly see things that weren't there before, like supernovae will go off on a measurable timescale, and you can see, I mean, a supernova went off in a relatively nearby galaxy very recently, and you can see that with an amateur telescope a lot of the time. So those things happen. I don't know if we can see any measurable things like mergers or rotation very much, but yeah, it happens on a longer timescale than we can really measure.
Okay. Please thank our speaker, Rachel Theios, for a wonderful talk. So, as I mentioned during the introduction, unfortunately, the weather is not such that we'll be able to observe tonight. I did bring down one of the telescopes so we can do an optics demonstration in the hallway if you're interested in seeing that. And in about 5 minutes, we'll set up and have our panel Q&A. So I encourage you guys to stick around and ask all the questions that didn't get answered to our panelists. Maybe Rachel will stick around as well. So thanks for coming. And we've got the schedule outside. If you want to come back to one of our future events, the next Astronomy on Tap is in a week and a half. The next lecture is in 2 weeks. So thanks for coming. All right, thanks for sticking around, everyone. We'll start our panel Q&A. Tonight, our panel Q&A is made up of a number of graduate students in the department. I'll also join in and chime in if I can help out in some way. But so I'll introduce each person, and then behind them is their name as well as a few topics that they're happy to answer questions on, although you're welcome to ask questions about other topics that aren't listed, but these are particularly ones that people are comfortable discussing. So Mia de los Reyes is a graduate student. She's comfortable talking about galactic archaeology, how to make stars, and shouting caps, galaxies. Nitika Yadlapali is a graduate student who specializes in astronomy instrumentation, and she's given some illustrations of different types of telescopes, both radio telescopes and visible wavelength telescopes, a variety of different types. Chris Bohenik is a specialist in fast radio bursts, a really interesting phenomenon that's been discovered in the last couple of years. And there's a radio telescope being built in Owens Valley that Caltech runs up near the Sierra for studying these things, as well as he's comfortable talking about pulsars and supernovae. And then Dylan Dong is a graduate student who is more comfortable with supernovae, star formation, radio astronomy, and then, of course, our speaker from tonight, Rachel Theios, who I imagine can talk about a variety of things that she spoke about during her presentation: galaxies, early universe evolution, observations in the UV and the optical, and then I'm Cameron Hummels, and I'll talk about other stuff if there are other questions. Okay, so any questions from the audience? Yes?
When is the last star expected to be born?
Okay, the question is, when is the last star expected to be born? I don't know if I know how to answer that. Yeah.
That's a hard question. I don't think any astronomers have made conclusive predictions for this because it's so far in the future, but my guess is it's on the... So people refer to the age of the universe today as a Hubble time because Hubble expansion has been going on for roughly 14 billion years. So I would estimate that it would be on the order of 100 Hubble times in the future, something like that. So on the order of 100 times the age of the universe. But it's a while because... yes, there's a lot more gas that can flow into galaxies to form stars, but also when stars age, sometimes they pump out a little bit of gas that can then go into making more stars, so it's kind of like a recycling process. But yeah, as Rachel correctly said, the expansion of the universe is accelerating, so things are getting farther and farther apart, and it's harder and harder to accrete gas in these sorts of structures. So the end point is like a bunch of black holes that are just away from each other, and it's a really boring place. It's much more exciting right now. Other questions?
Yeah, this is kind of off topic. There's a cable TV program on how the universe works. It's got lots of beautiful visuals and bush bangs, CGI graphics, and the whole thing. And I'd like to know how these young people view that type of outreach, educational outreach, published today. To me, it's just entertainment. Do you think that there's any real education that's taking place here?
The question is, on cable television, there are a number of programs, of which one is How the Universe Works, and do people agree that this is useful in terms of education, or is it primarily an entertainment source?
Just go down. Yeah, so personally, I grew up watching these shows. I love them. Even if they're not like the most scientifically accurate things, they get people excited about science. And science is always something that you can just learn about on your own, right? And so the excitement, I think, is what matters. But maybe other people have different opinions.
No, I reflect that opinion.
Yeah.
There's a huge variety in terms of the quality of the information that's being presented in different programs. I'm not familiar with this particular program, but there are some classical programs like Nova, and there was Carl Sagan's program and Cosmos and these sorts of things. And there's a huge amount of information that is accurate in those programs. So yeah, at some level, it's really good for just increasing enthusiasm for the sciences through entertainment. Much better than watching some of the alternatives that are out on television. But yeah, there is a lot. There are a lot that have a lot of viable information in them. So
I will say that shows that are on a channel who I will not name, but that rhymes with the Blistery channel, those are probably not super accurate, especially if they mention aliens. Just love the Blistery. Are there any other questions? Do we have a question from a kid? Is that a question from a kid? Yes. Okay. What are pulsars? Excellent question. Chris.
So pulsars are neutron stars, which... So the sun is really big, right? Like you look up in the sky and it, with proper protective sunglasses at the sun, and it takes up like a big angle. It's really far away, so the sun has to be really big in order to appear in the sky like that. So imagine if you took the sun and something as massive as it and scrunched it down into the size of Los Angeles. And that is pretty much what a neutron star is. And these neutron stars emit, they're like cosmic lighthouses. So they have two beams of light.
Do you want to draw a picture?
Can I get a... volunteer artist. Yeah, so you have a thing that's like the size of a city that's emitting really strong light in two different directions. And every time the beam of light crosses our line of sight, so you see a little pulse, and they're very regular things. And you can actually predict the arrival of the next pulse to within like a very small fraction of a second. So they're like both cosmic lighthouses and cosmic watches.
How do you make them?
Supernovae. Yeah, they're stellar remnants. So when a star bigger than 10 times the mass of the sun explodes, it might leave behind something like a neutron star. Yes. In the back, you. Yeah.
So the question was, how common are collisions of pulsars and black holes? As far as I know, nobody's ever seen pulsars necessarily colliding to each other, but we've seen once two neutron stars, which were not pulsars. Well, actually, we don't know whether they're pulsars, but we saw two neutron stars collide, and that produced a really cool explosion that emitted gravitational waves that you may have heard of in the news a couple of years ago. Black holes, it turns out, are much more common. Like stellar mass black holes colliding into each other is probably like 10 or 20 times more common than neutron stars colliding. But they do happen. Within the span of a few months, within like 100 million light years, we saw like 10 of them. So, yeah. So the question was, what happens to the magnetic fields when these extreme objects collide into each other? So for some background, neutron stars are have got some of the highest magnetic field strengths that we know of. It actually, like if you put an atom near a neutron star, the atom will get stretched out because the magnetic field is so strong. And one thing that might happen is that these magnetic field lines get twisted. And when you have material that's flowing into like the newly created black hole from the collision, some of that material gets ejected out along the magnetic field lines and produces these sorts of jets that are moving at close to the speed of light, like 99.99999% the speed of light. And these are known as gamma ray bursts. So magnetic fields are important. Yes. Yeah.
So the question was, as astronomers, obviously we always want our instruments to be better than they are now, which is a 110% true statement. And the question was, what technologies are we hopeful about developing in the next several years that would make astronomy better? And the answer to that is very broad. There's a lot of them across lots of fields of astronomy. Detectors are a really big one. Right now, a lot of detectors are not very efficient at capturing light. So you have your camera, and you have some amount of light coming into it, And it would be spectacular if all of the light coming into our camera was recorded on our cameras. But that efficiency is, and correct me if I'm wrong, but I think that efficiency is around 15 to 20%. It's not something very high. So improving detector efficiency is something that people work a lot towards. Ways to make mirrors bigger, or just having bigger mirrors, is something that a lot of work has gone into over the last several years. How faint of an object we can detect using telescopes you can detect fainter objects if you have bigger mirrors, because you're just collecting more light. And so ways to make mirrors larger and more reliable have also been a really active field of research. And if anyone has been interested in gravitational waves, LIGO has probably the coolest technology advancements happening right now. And they do everything from making sure nothing in their structure is shaking to making sure that so LIGO is so advanced and so precise of an instrument that I read an article recently about how they're concerned about when the laser light hits their mirrors, it's going to move the mirrors slightly out of alignment just from the pressure of the light. So that's the level of precision that is available to people at LIGO, and they're still trying to make that better. So just ever better precision is what we're always hoping towards there. I don't know if you were looking for a more specific answer, if there's something specific you're interested in that I can talk about. Yeah, sure, we can talk after. Any other questions?
We had one from up front here.
Oh, yeah. Qualified to talk about black holes.
Okay, so the question was, when you have a black hole, Einstein's theory of relativity predicts that at the very center of the black hole, the density blows up to infinity. Is it really infinite in the center? And the answer actually is we really don't know. There is no way to actually probe inside what's called the event horizon of the black hole, like the skin of the black hole. There's absolutely no way that any light can escape. And it's not just any light. There's absolutely no way that any information of any kind can get from the inside of a black hole to outside of a black hole. And since we don't actually live in a black hole, we're never able to access any information from inside. And so you can write down a lot of equations, you can make lots of predictions, but there's no way to actually test what's buried inside. There are some reasons why physics would break if there are infinities inside, but maybe it's just hidden. Maybe it's cloaked by the fact that it can never affect anything that's outside of the black hole.
So when the question was kind of what was the nature of progress of LIGO? Was it instrumental, or was there one giant breakthrough? And the reality is, when the idea for LIGO was proposed, a lot of the technology that is used in the version of LIGO that first detected gravitational waves, it didn't exist when LIGO was first developed. And a lot of times that's the case for major projects like this. You'll say, this is the goal I want to achieve, but these are all of the technology developments that I need to make sure we can create first. And that's a lot of why LIGO took so long to achieve success, is they were kind of waiting for technology development to catch up with their ideas. And most of LIGO's problems were just outside noise interrupting their measurements. So LIGO, for scale, the scale of the measurement that they're trying to make is a fraction of the size of a single proton. So they need basically unfathomable precision, although now fathomable because they have results. But they are, if you ever go to one of the LIGO facilities, they have exactly what you think a fancy science facility would have, a wall just filled with monitors, monitoring all different sources of noise. They have one for like seismic waves, one for trucks crossing on the road. The speed limit on the road for several miles around LIGO is like 20 miles an hour. Like, you have to pay a lot of money if you go faster than that because you're ruining their experiment. They have monitors recording how much air is in the vacuum chamber, because if it's not a perfect vacuum, just the air vibrating around the chamber will cause a lot of noise. And all of the different ways that they could measure this and beat it down were what eventually led LIGO to success. But a lot of the ways to do that were still in progress as LIGO was being built.
There was one breakthrough among many that took place that wasn't just about the detector and the sensitivity of the detector, and that was what to look for in the signal. So rather than just having these set up and knowing what to look for, because it wasn't clear what the signal would look like, there were a number of computer simulations run to try and predict what the signal would look like when different black holes of different masses and different characteristics merged. But that wasn't even possible like 15 years ago. None of the computer simulations could appropriately account for all of the relativistic effects when these things occurred, because, as we already discussed, the interior of black holes are really wonky and don't behave by nice laws and such. But there was a breakthrough that occurred on the order of 10 or 12 years ago that finally allowed computer simulators, many of them here at Caltech, to be able to do these predictions of what the signal would look like. And so I know that also played into, obviously, the main thing has been the sensitivity of the instrument, but also knowing what to look for in the signal was a major step forward.
And I also just want to add that a lot of these technological improvements are still ongoing because they're working on upgrading LIGO, and they're also working on, there's a new proposal for LISA, which is the Laser Interferometer Space Antenna. There we go, antenna. I was going to say array, but that's fine. So it's basically LIGO, but in space. And so they have to think of all new ways to, suspend test masses in space and send lasers in space, which is great. That's what we all really aspire to as astronomers. And they also have to run these calculations again because LISA will be sensitive to an entirely different frequency than LIGO is. And so we'll have to, do new modeling to figure out what we should be looking for with LISA. Cool. Question here?
Yeah, my question is for Chris. Sorry, basic, but I've never heard the term fast radio bursts. Can you tell me about them, please?
I would love to. The question is, what are fast radio bursts? The short answer is we don't know. The slightly longer answer is that we see millisecond-long pulses of radio emission coming from distant galaxies. So the fact that they're a millisecond long tells you something about the source's size. Whatever it is has to be able to produce some coherent bit of information within a millisecond, which means it's probably a compact object like a black hole or a neutron star. But there's a lot of effort going into figuring out what they are, and my thesis is essentially building instruments to look for these things. So not only is a lot of effort, but a lot of money is going into figuring out what they are. And the next frontier is, so I say they're coming from distant galaxies, but we don't know which ones. And what type of galaxies fast radio bursts occur in could be a clue as to what they are. So we're building instruments to find out which galaxies they come from in the hopes of figuring out exactly what they are. Radio telescopes aren't. So the question is, why don't we know which galaxies they're coming from? And it's because traditionally they've been found with single dish radio telescopes, which aren't very good at localizing things. So essentially what you get from a single dish radio telescope is 1 pixel of your camera. So you just get a measurement of the total power. And
It wasn't meant to be a heart. It was just meant to be a source. But this is like the pixel over a huge region of area.
yeah, so within that pixel there are many galaxies, and we can't pick out which one the fast radio burst came from.
What's some of the preliminary speculations?
I think the leading theory is weird magnetar stuff.
What's a magnetar, Chris?
And a magnetar is a neutron star with an especially high magnetic field, about 1,000 times stronger than a typical neutron star. And I think the history goes like, if you don't know what it is, fit a magnetar model to it. But we know that neutron stars and magnetars also emit millisecond-long bursts. And magnetars especially do some of the, like, they look like fast radio bursts in like how their emission looks as a function of frequency. And they have enough energy to produce the amount of fast radio bursts. They have enough energy to produce a fast radio burst. And one fast radio burst we know repeats, which tells you it's not a cataclysmic event like a star exploding. There are 2 now. I need to get used to that. Yeah. So that tells you that it's not something that happens once and then you're done. And magnetars happen more than once. Like, there's lots of opportunities for magnetars to do weird things.
I saw one in the back.
Yeah, so yeah, I say that some of them repeat. They don't have an underlying periodicity, so they're not predictable like a pulsar is. They seem to turn on and off. Like, you'll observe with your telescope for an hour and you'll see 10 bursts, and then you'll keep going back to it for months and not see anything. And then one day then like a week or 2, it'll turn back on and you'll see a bunch of bursts and then it'll go off. Yeah.
So how much of your time do you have to spend refuting conspiracy theories who keep claiming that fast universe are, from an alien civilization, and supposedly they only last for 1 millisecond, right? So they have the technology, but it's only going to last for 1 second.
So here's a question for you. Why do aliens all have the same technology? Yeah, I guess when I talk to people, it generally comes up, but I don't think anybody really takes it too seriously. There was a paper on a couple of years ago by an astronomer at Harvard who who speculated that what if fast radio bursts were, suppose an alien civilization had a technology to move spaceships like close to the speed of light and they powered them through shooting radio waves at them, and claimed that a fast radio burst would be like the moment between when the spaceship has exited the field of view of your emitter thing that's moving it forward, and when they turn it off. But that has a testable prediction that you should see like the diffraction pattern of the sail of the alien spaceship in the burst, which I guess if we see that would be interesting. But it's yeah. Yeah, it's actually a pretty interesting paper to read, but I don't think it should be taken too seriously.
You're all aliens, right?
Oh, yeah. They didn't tell you that beforehand?
Yeah.
Regarding aliens, there are ongoing attempts to detect extraterrestrial life, within the microbial, perhaps within the soil of Mars, or perhaps future Europa mission or something like this. But barring the detection, direct detection within our solar system, there is a possibility of indirect detection.
So the question was, one way that we could possibly detect life is on exoplanets. So by characterizing the atmospheres of those exoplanets and figuring out what's in them, what is sort of the smoking gun that there could be life on these planets? So one thing that exoplanet scientists, none of us are actual exoplanet scientists, so these are recorded, so I hope no exoplanet scientists come after me for saying things. But one signature that people try to look for is water. If we see lines from water in the spectra of these exoplanet atmospheres, then that could be a clue that life similar to life here on Earth might be there. And if those exoplanets are also in the right temperature range for life similar to life on Earth to exist, then that could also be a clue. Part of the problem here is that it's entirely likely that life on other planets does not look anything like the carbon, nitrogen, oxygen, hydrogen-based life that we have here. So it's kind of hard. We don't really have the imagination, I think, right now, or the sensitivity. So we need better telescopes. Please give us money.
To say there's one definitive thing that you can say that if you see this in an exoplanet atmosphere, that means there's definitely life there. I remember a couple years ago there was a paper trying to come up with a list of signatures that would be like, I don't know how to produce this without life. And then in the subsequent years after that paper was published, more were published saying, here's how you can produce this feature that was proposed to be only life with only geologic processes. So I think that's a really difficult thing to say.
Michael's a grad student. He's not just a random person in the crowd. He actually studies exoplanets, so maybe I should have watched that.
Presentation had a really nice picture of the black hole. I guess we can thank Kip Thorne for that.
Oh yeah, Kip Thorne.
But we've been reading for a number of years now that pretty soon astronomers will be up.
Do you guys know about that? Okay, Dylan.
Yes. So, in fact, there is a... Okay, so the question was, are we going to be able to image the event horizon of a black hole soon? And yes, there's a collaboration called the Event Horizon Telescope Collaboration. They were supposed to release the results earlier sometime late last year. They're sort of delayed, but hopefully this year. They have data that they took, I believe, in 2017 that, in principle, should be good enough to be able to get at the black hole at the center of our Milky Way. And so we're all excited to hear about news from them. They're being very, very tight-lipped right now. So hopefully some press releases coming soon. Mm-hmm. Yeah.
Yeah, the ratios were the same, I believe, but it's just that which one had the most influence. I mean, it was still the same at cosmic noon, but later on, the dark energy will exert the most influence over everything, but it'll still be the dominant, I mean, the same ratios of everything, I think. Is that right? We're not sure?
Yeah, that's right. They scale differently with A, right? And so,
well,
sorry, we're deliberating. We're trying to remember our cosmology class. Cameron, do you remember like how so dark energy should be a constant as a function of like the size of the universe, but then constant density, but then dark matter changes as like 1/8 of the third or something like that. Yeah. Yeah, no, it's not right because. Yeah. Okay, actually, yeah. So now I remember. So basically, dark energy is basically the same amount of energy per unit volume at any given time. Dark matter, however, gets diluted as the universe expands. So if the universe increases by a factor of 2 in its radius or its diameter, then the volume of the universe is going to increase by a factor of 8. And so the dark matter that was already there just gets diluted by a factor of 8, right? So really what you're looking at, what people mean when they say 70% of the universe is dark energy and 24% is dark matter and 6% is matter, what they mean is that in any given like volume, how much like of the energy density in that volume happens to be that thing, right? And so the total amount of dark energy is going to be the same in that volume, but dark matter and regular matter are going to get diluted as the total size of the universe expands, and they're going to drop, right? And so the universe is becoming more and more dark energy dominated because of this. Mm-hmm. Yeah. Yeah. Uh-huh. Uh-huh. Yeah. It turns out that there's... Yeah. 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 Okay. Yeah, congratulations. You've managed to make us all, scramble to remember our cosmology class. In fact, actually, what Mia is drawing on the board is that there's an additional component of energy density that people don't talk about usually because it's so small in the current universe. It's something like, I think, 1 part in 1,000 or 10,000 or something like that. And that's radiation, right? There's energy carried in just like starlight, in the cosmic microwave background light. And it turns out that in the very, very early universe, that was actually the most important source of energy density in a given volume, was radiation. However, radiation drops for various reasons as the size of the universe to the fourth. Matter drops as the size of the universe to the third, and dark energy does not drop at all. And so radiation now is pretty much negligible, but in the very, very early universe, it was the most important thing out there. Yeah, in the back.
What kind of stars are in the center of the universe?
The center of the galaxy or the center? You said the center of the universe. Well, okay, so the universe doesn't have a center, really. We don't think there is a center to it. Okay, so that analogy has a flaw in which the flaw in that analogy is that the bread has a boundary, the universe does not, as far as we can tell. So the raisin bread analogy is flawed. We don't think there's actually a center of the universe. But as to what the stars in the center of our galaxy look like, they're actually predominantly older stars. Which is maybe surprising, but we think that things collapsed in there very early on and then formed all these old stars, and then most of the new star formation is occurring in the outside of the disk. So that's like a complex process, but yeah. Is that anyone, Cameron, want to talk?
So you had a couple of really good questions all bundled together. So Rachel did an excellent job of addressing there's not really a center of the universe that we understand. We're effectively at the center of our universe because it's the center of the observable universe, and we're the ones observing. So it's in our light cone, we are the center, but that doesn't mean that we're actually in the center of any true physical structure. But there was another question that you asked in there, and that was the first stars to form in the universe were seemingly very different from the stars that both Rachel talked about today, as well as the stars that are forming around us today. So these are called the first stars. It seems no one has conclusively demonstrated that they've observed these things because they're so the light coming from them is so far away, or we don't know if they've survived to present. If they did exist, as you pointed out, they would have very little chemical enrichment, so they'd have very few what astronomers call metals in their stars, and show that in the light that we see. And we see some very metal poor stars, but they aren't conclusively existence of these. But we do think that the stars that formed at that time were very massive, much more massive than like the sun, for instance, something on the order of 100 times the mass of the sun. And because of that, we think that they would die relatively quickly, and when they did, they'd have a very big explosion, which our sun won't have. It won't turn into a supernova, but we believe that these first stars probably exploded pretty shortly after they formed. But this is definitely an active field of research that both theorists and computer simulators are trying to simulate the evolution of these systems and then make predictions for what observers should go and look for when they observe very distant and early objects in the early universe. So I hope that addressed one of the questions that was wrapped up in there. But it's really good because, yeah, first stars are super interesting. So the question is, what's the spatial distribution of dark matter across the universe? Oh, yeah. So the question, in case you didn't catch, was how has the spatial distribution of dark matter changed over time, right? That is excellent. I gave a lecture on this 2 months ago, and I showed cool videos. So if you go to our YouTube page or whatnot, you can watch the video. But essentially, in the very early universe, things were pretty uniform. There wasn't a lot of variation in the density of structures. It was kind of like a big, what's a good analogy for this? A big swimming pool. No. Very early on, is this pen okay? Oh, good. Okay. Very early on, if you take a box of the early universe, it was pretty much all the same density of stuff and the same temperature of stuff. But there were very slight perturbations from this, very slight overdensities, but very slight, like 1 in 1,000 parts a little bit more massive or dense, and then 1 in 1,000 parts a little bit underdense. But what gravity does is it accentuates these overdensities and underdensities. Gravity is an attractive force. That's why we're attracted towards the Earth, being pulled down because the Earth has mass. And so essentially any two objects that have mass, this microphone and this pen both have mass, they're attracted towards each other. Of course, the attraction right here is quite small, but what you get is the collapse of things that are overdense initially. And so over time, the stuff near these overdensities starts to fall in towards it. If you can make out my arrows pulling things in towards it. And so gravity enhances these overdensities and primarily in the dark matter, although also in normal matter like what we're all made of. And then over time, you build up these dense structures, and that becomes the location where galaxies and stars tend to form, is in these overdense locations. And you evacuate the regions in between them, which are now what we consider voids, where there's very little material there. And so this is usually referred to as the cosmic web, because it's kind of like a web-like, spider web-like structure of filaments in between filaments and crossing filaments. You have nodes where you'll tend to find more formation of densities and a formation of galaxies and stars and so on and so forth. I realize that was a long-winded and kind of circuitous discussion, but yes, the dark matter distribution has changed over time, primarily by changing from a really uniform distribution of matter into a very clustered distribution of matter. And that's what's responsible for the formation of stars and galaxies and everything we see in the universe. Make sense? Okay, cool. The gentleman in the back first. No, you. Oh yeah, so we get into entropy. Well, no, actually in this case, the uniform distribution of matter, because it's very small in volume, because remember, there's also the expansion of the universe as well. We are increasing in entropy. The second law of thermodynamics increases entropy, increases the disorder of the universe. And so, yes, at the time of the Big Bang, we were at the lowest entropy state of the universe, and we are increasingly getting more and more disordered, more and more high entropy. Your ice cube will always melt when it's in hot water. You won't take a tepid glass of water and have an ice cube form out of it and then steaming, boiling water as well. It was smoother, yes. Well, order is not, yeah, so entropy is not the exact same thing as apparent order. I know a lot of times we use that. In fact, I just did in my example. But entropy is simply the number of states that are statistically similar to each other available to a system in different orderings of that system. And Dylan is going to write the equation for entropy. Oh, no, he's just writing down what I'm saying. Okay. So I don't think it'll be helpful here. So as the universe expands, we have more space, effectively, for the matter within that space to occupy it, and more possible configurations of the matter in that space. So really the expansion of the universe definitely plays into the role of how entropy can increase with time. Yes, the early universe was very uniform, so you might think of that as a very high entropy state, but in this case, because we also take into account the expansion of the universe, it's actually the lowest entropy state available to us. So we haven't broken the second law of thermodynamics. We're still A-okay. Any other questions? Gentleman here?
It's okay.
We've always seemed to kind of assume that our galaxy is like the Andromeda galaxy. How do we know that it is? If we can't see it from outside, how do we know that it's like the Andromeda galaxy? We can't see through the disk, the dust and gas at the center, so how do we arrive at this conclusion? Well, first of all, are there any astronomers who think that maybe it's not like the Andromeda galaxy? Maybe it's something different. Or how do we know that it is like the Andromeda?
Great question. All right, so the question is, how do we actually know that our Milky Way is like the Andromeda galaxy? Because we can't see. Sure, okay, all right, that's fine. Yeah, no worries. So how do we know that the Milky Way is like the Andromeda galaxy? Because we can't see through the own disk of our Milky Way. We're in a system. And so with the Andromeda galaxy, we're outside the system, so we can see the whole thing. We can see there's a disk-like structure. But we're inside our own Milky Way, and we can't see out through the disk, right? So when we look up at the sky and we see the Milky Way, we just see a band. So are there people who think that the Milky Way is not a disk? Not really, no. I think most astronomers agree that the Milky Way looks like a disk. And the reason we know that is because...
Maybe like a barn spiral?
Oh, yeah, that's a good question. So how do we know the structure of the Milky Way? To more detail than just the fact that it's a disk.
Yeah.
So the first the first person to try to do this was this guy named Shapley, I think. And what he did was he looked at the sky and he counted stars in every direction. Was that Herschel? Okay, it was Herschel, my bad. It was some person. And he saw something that looked like this. Caroline Herschel. That's it, that's what he saw. And so from this, you can't really tell what it is. But since then, our measurements have gotten a lot better. Recently, I think most recently, the Gaia satellite, which was sent up by the European Space Agency, has measured the positions and the velocities of 1 billion different stars from where we are. And so what that does is that gives us a lot more information about the structure of things. So now we can actually see stars moving together, and we think that based on how we map the stars, we actually do think that it is a barred spiral galaxy. You can see outlines of a stream of stars where the sun lives in. Does that make sense?
Yeah, but how do we know how many arms there are in the Milky Way?
We don't, okay, so in science I think it's hard to say that we know anything for sure, and it's especially hard in astronomy because there's always something new. But we're pretty sure that we know the number of arms based on these exact kind of mapping measurements. We can't see through to the other side of the disk, so as I said, this is, a best guess, but we can see the outlines of the outer parts of the arm. Does that make, on the opposite side of the galaxy? What?
You don't mind me asking?
Mm-hmm.
Why did we just assume that it was like the Andromeda galaxy? Because I guess this is more about the history of astronomy.
Yeah.
It seems to me that they just said, oh, well, it's like the Andromeda galaxy. Why did they make that assumption to begin with?
So I don't think they made that. So, all right, initially when we first discovered galaxies, there was a huge argument about whether or not galaxies were separate systems or if they lived in the Milky Way and were just kind of like fuzzy blobs, because this was back before telescopes were good. So everything looked like a fuzzy blob, especially galaxies. And so this led to what is sometimes called the Great Debate, which is basically two guys sort of going at it. And, and the guy who won was the guy who actually thought that the galaxies were in the Milky Way. And he was wrong. So galaxies we know now are separate systems. So initially we didn't actually believe that the Andromeda galaxy was a galaxy. It was thought to be a nebula, just a cloud of gas in the Milky Way. And it was only much later when we got better images that we were able to tell that the Andromeda galaxy is actually a separate system. And I think a lot of people assumed at first that it was very different from the Milky Way. And it's only now that we've been able to do this kind of mapping. And this is, we've had pretty good maps of the Milky Way for a while now. Gaia is the newest, confirmation of what we thought we knew. But
we don't have maps of what's on the other side.
No.
Okay.
So we can still see like okay. Rachel, do you want to attempt to answer this question? I feel like I'm doing a terrible job trying to explain this. So.
I don't have anything better to say. So I don't know if we can see the other side, but we can definitely see through the dust into the center with the infrared, right? So the dust doesn't obscure the infrared as much as it does the optical. Dust has a wavelength-dependent effect on the light. So you can actually look at the galactic center in the infrared. And so we know that in that sense it's similar to Andromeda. It has a central bulge of stars with a plane-like structure around it with active star formation. And we can tell where the new stars are forming, where a lot of the gas is distributed relative to Andromeda. It's not so much about the star count. I mean, it is about the star count. There's more to it than that. And I don't know if that's a better answer, but yeah.
So we also don't just see Andromeda that looks like this. We also see a lot of other galaxies that have the same spiral structure. And so the fact that our galaxy is a disk-shaped galaxy suggests that it also has the same spiral structure, if that makes sense. And it's also not just, so the other interesting thing about the spiral arms is that they change the potential of the gravitational potential of the galaxy. So because the galaxy has a unique shape, it has a unique, gravity acts on things in the galaxy in a unique way because of that shape. And so we can actually trace that too. And based on counts of stars and observations of gas and how things behave gravitationally, we are pretty sure, we're very sure that the spiral structure of the Milky Way is a spiral that's barred. Yeah?
At cosmic dawn, were galaxies primarily diffuse and irregular, or did you see nice spirals?
I mean, you see some ellipticals and you see things that look like spirals in every other way, but they don't have a nice, beautiful spiral, a grand design spiral structure like they do today. So I did show in my talk a few images of galaxies at cosmic noon, and they do look really irregular. At cosmic dawn, I think there are not very many galaxies at all. It's just like when the first stars formed, and there are maybe some galaxies, but they would be very diffuse. They would be very irregular. I think the really pretty spirals formed later, but yeah. Any more questions? Yeah.
The question related to the discussion that we had previously about the formation of structure in the early universe and how initially there were slight overdensities in the early universe and gravity caused more matter to fall onto the structure. So why is it that we have now a cosmic web of filaments and walls and points instead of just a series of overdense points? That's roughly the question. Well, it's primarily because the distribution of the points is pretty asymmetric and pretty chaotic, pretty random. And matter will tend to, because gravity accelerates things based on the proximity to an object. So if I have a overmassive object of one thing here, and then we'll pretend that this is a similar overmassive object, then the stuff that's very close to this falls in first because the gravity force falls off with the square of the distance. And effectively you get this web of structure because things fall in, let's see how I can explain this. There are essentially three different overdensities. There are zero-dimensional overdensities, which are points. There are one-dimensional overdensities, which are filaments. and there are two-dimensional overdensities, which are walls. And it turns out this is an active field of research that a lot of computational models are trying to address. If you take galaxies tend to sit at the nodes, the zero-dimensional structures, and along in the filaments, the one-dimensional structures. But the gas, as it falls in, usually gets wrapped up in its angular momentum in two of those dimensions, and one, it falls in along one much more effectively. So usually a galaxy that's, let me draw this. A galaxy that's like that, where its angular momentum is keeping it aloft, right, from its rotation. Gas has fallen in, perhaps unsurprisingly, along that direction. And so it's almost as though the filament is kind of aligned with, the filament is aligned with is perpendicular to the angular momentum vector. And yeah, I just got into some science there, and some jargon. The root of your question is simply because matter carries angular momentum, and gas and dark matter carry that angular momentum when they fall into these points. So when material falls into one of these points, it doesn't just stop when it gets into the center of it. It continues. And ultimately all of the distribution of these of the gas and the material in the early solar system, in the early universe had some net rotation in localized regions that results in falling faster in effectively one direction because you'll get rotation that builds up and provides support. In observations, I think it's really hard to see. Simulations do predict that again, this is an active field of research, but simulations do predict that there should be some alignment along filamentary structures and what the angular momentum vector and the rotation of the different galaxies that are present. But I don't know, I would have to ask Rachel if observations actually bear this out.
There have been claims of observations of this, but I don't think anything has been conclusive enough to be accepted by the entire astronomical community.
People look at the distribution of satellites around the Milky Way and the Andromeda galaxies, and there are claims that maybe there's some disk structure of various different satellites that are all aligned, indicating some preferred orientation of the galaxy, or for other galaxies as well, but it's tricky. It's tricky. Sorry, that was again very long-winded. I'm a very long-winded person. That's my nickname. Are there any other questions? We probably have time for a couple more questions before we need to finish up. Yes. The question is, what's the next most viable planet that we could live on? Do you guys want to talk about it?
It's Mars. You want to talk about it?
Yeah, so this is actually way back when I was a freshman undergrad. I worked with this professor whose main research was speculating if we lived on Mars, what kind of habitations we would need to build. And I found out that that's actually a fairly active area of engineering research. People are really interested in how to build, how to transport, and then build structures on Mars that could support human life. And I was really interested to watch The Martian. Have you seen The Martian? It is a really great movie with Matt Damon and other people, but mostly Matt Damon. And the premise of the movie is he is an astronaut. He and his team get sent to Mars. There's a big accident, and the team leaves on an escape pod, but he gets stuck, and he's living in this Martian habitation that was sent to Mars with the astronauts. And there were, interestingly, a lot of similarities that I saw with research that I had done as an undergrad. And I think that scientists who think about this are playing with the idea of, if we have to move off of the Earth, Mars is a good place to do that, because there are a certain elements on the surface that we could use to construct structures, like the Martian dust and stuff could be formed into structures viably. And it's close enough that we can send people there, and it won't take hundreds and hundreds of years, which is also a big plus. Plus, we've sent other satellites there, which means we know how to get there, which is another big plus. So, yes, RIP Mars Opportunity rover, which provided us with 30 times the lifetime we expected it to. But that's an aside. Yes, died yes. Well, it was confirmed to have died yesterday, but they've been trying to reestablish contact with it for many months. So, yes, the answer is Mars, if we're going to live somewhere. So the question is, how will we get water to Mars? And I learned that a really favorite idea is to get water from asteroids and then redirect it to Mars. That's a really popular idea if we were going to habitate Mars. I don't know.
So the question was, is there water underground on Mars, under the surface? Because there has been a lot of evidence for surface features that are consistent with the presence of water in the near past. But the answer is we don't know. This is definitely an active field of research, both from a scientific perspective as well as, like you're mentioning, a possible future destination for us. And since water is so necessary for us, both to drink as well as you can break H2O into hydrogen and oxygen and use that to breathe, it would be nice to not have to bring all of our water with us, but actually use it from some place in situ. And we don't know. Lots of planetary scientists and NASA missions and other space agencies programs are trying to figure this out, but we don't know. We hope so, but we don't know. The polar regions are cold. There is primarily in the Martian winter you get polar ice caps. It's not usually liquid water. It's usually carbon dioxide. It's dry ice that forms there. But yes, that would be another place to look for water. I wish I had a better answer for you. So it's not really a question, but the idea was just floated, given that one of the previous questions was asked, what is going on in the interior of a black hole? We can't really speculate on it because we don't exist on a black hole and information can't be transferred out of the black hole, but one of the audience members proposed that maybe since the Schwarzschild radius for the universe, which is essentially on the order of the event horizon of a black hole, is the size of the universe, maybe we exist in a black hole. Maybe the whole universe the observable universe that we sit inside, is actually a black hole. I don't have a lot to say about that, but maybe Chris does.
So if we live inside what we think of as a black hole and there's a singularity at the center, then if you are inside of the black hole, it is your fate to end up at the singularity. So if the universe is a black hole, everything should be moving towards a singularity, and it looks like everything is moving away from everything else.
How could there be a black hole inside a black hole is my question. We see black holes exist.
It's actually a funny quirk of the math of general relativity that when you're, and I don't know, like this is just a theory, right? But when you're inside a black hole, it turns out that the time coordinate switches to the space coordinates, and so it is as inevitable for you to fall into the center of the black hole as it is for time to move forward. It's a cool analogy that my professor told me once. Yeah. Yeah. There's a hand in the back. Yes. Yeah. Go. Mm-hmm. Okay, so the question was, suppose that there is a planet that was, 13 billion light years away. If they looked up into the sky, what would they see in terms of the cosmic microwave background? And actually, when the universe was that young, so the fact that we see it 13 billion years away means that it existed at that time, right? The light from that planet happened to have reached us from that time. And so back then, the universe was super dense, and the cosmic microwave background was actually a lot hotter. And so, 13 point something billion years ago, the temperature of the microwave background probably was somewhere that wasn't actually in the microwaves. It depends on exactly 13.1 billion years, but maybe it was a cosmic optical background at that time, and so, or maybe a cosmic infrared background. What do they see now? Oh, well, let's say that they survived being in that dense, hot universe back then, and 13 billion years have passed. They see the same cosmic microwave background that we see. Everywhere in the universe looks the same as far as we look. Not quite sure I followed that one.
But we can't communicate with that population. So if Rachel is planet X, that's 13 billion light years away from me, it may be, yes, that at present day she sees a similar cosmic microwave background, not identical, but similar to what I see, but there's no way that she can communicate that information to me, because she would have had to have sent that signal 13 billion years ago for it to transfer across the 13 billion light years between us. I mean, we're extrapolating. We can only speak to what's going on in our observable universe, and we predict that from her perspective she would see similar statistical properties to the cosmic microwave background based on how we know the universe existed at that early period in time, but we aren't there. Well, we aren't observing it. It's extrapolation from our experience here. Do you guys have anything to add on that? I don't know. It's a tricky question. Okay, we should probably wrap it up there. with a difficult question. Thanks for everybody for